Hello, my name is Michael West, and today I will be giving a summary of my paper that was recently published in the Journal of Neurophysiology titled Kinematic Hand Synergies Differ Between Reach and Grasp and Functional Object Manipulation. Today, humans still outperform robots in physical interaction tasks, especially those involving objects with complex dynamics. This is heavily observed in manufacturing, where much of the manufacturing process today can be done automatically by robots, as shown in the video on the left. However, when you have an electromechanical system that needs cables to be assembled, routed, and housed, this task is known as wire harnessing. And as shown on the right, due to the complex and non-rigid nature of wire harnessing is largely done manually by humans. And this manual process creates a bottleneck in the assembly line and slows down production. With the goal of increasing production, the team I was working on proposed moving towards a system that uses robots to assist in wire harness installation. However, before we add a robot collaborator, it's important to first ask, what are the humans doing so that we can better assist them? Moreover, the prior wire harnessing task is an example of what we call the paradox of human performance. In my research, I study how humans manage physical interaction. Specifically, I want to understand from a control standpoint, how do humans control movement so that we can implement this on robots? In the video shown on the left, you can see humans successfully managing their everyday complex physical interaction tasks, while on the right, you see some of the most advanced robots doing these tasks in a much less spectacular fashion. And more or less, these videos on the right are the state of the art in robots today. What makes this more interesting is when you look at humans' wetware and hardware. We have actuators that are an order of magnitude slower, communication that's 6 orders of magnitude slower, and feedback delays that are 2 orders of magnitude greater. So it appears we're doing so much more with less. And I believe to bridge this gap between human and robot performance, we must study human motor control, perception, and learning. However, studying humans is difficult. We are a highly complex biomechanical system with more than 600 actuators and 200 joint degrees of freedom. However, the idea of kinematic hand synergies help address this challenge. Synergies are the result of dimensionality reduction. For example, if we take the equation on the screen, theta equals phi as a function of del, theta may represent the high degree of freedom feature space. Here, that may be the relative anatomical joint angles, and del is a possibly neural command that has fewer dimensions than theta. And phi is a kinematic mapping between del and theta such that we can now use a lower dimensional del to control the high dimensional phi. The best way to internalize this is to think about how we use our own hand. The hand has more than 20 joint degrees of freedom, as shown in the graphic on the left, yet we rarely ever control each one of these joints individually. Rather, we control many of them simultaneously in a coordinated fashion. And this coordinated fashion is known as a synergy. And in fact, in the human hand, it has been found that these two synergies account for upwards of 75% of the variance in hand posture, which is a great reduction in the original 20 plus degrees of freedom system. The graphic on the right can help you internalize the motion of these synergies, while on the horizontal axis, we see the first synergy, which is often akin to a power grasp, and on the vertical axis, we see the second synergy, which is often akin to a pinch grasp. Upon dimensionality reduction, if you end up with great synergistic reduction in degrees of freedom, you might incorporate them into your system that looks something like the block diagram shown here, where you have a synergistic controller whose synergy-based degrees of freedom are significantly lower than actual degrees of freedom. For example, you might use 2 synergies to control an entire hand. Or on the other hand, you might use these 2 synergies to inform the design of your robotic hand. However, one limitation in prior work of this is the fact that researchers often limit their study of human dexterity to simple tasks such as grasping. Well, if we base our robot controller on grasping studies, then you can imagine that we might not be able to perform the great dexterous manipulation tasks as humans are capable of. For example, in your controller, you might incorporate synergies used in the picking up of a screwdriver, and you can imagine that if the goal is to screw with that screwdriver, which incorporates very different kinematics, you might not have given your robot the correct subspace of control. This gap leads to 2 open questions, the first of which is, do kinematic synergies emerge in the human hand during functional tool use? And second, if so, are they the same synergies that emerge during the reach and grasp of those tools? To answer these questions, subjects performed 2 experiments while wearing the cyber glove, which is a soft glove that measures 23 relative joint kinematics of the human hand. In the first experiment, we measured reach and grasp kinematics. Shown on the left, subjects reach and grasp an object that is commonly used in wire harness installation. Those objects include scissors, screwdriver, zip tie, and a wire harness, and they were specifically instructed to grasp the object as if they were going to use it. In the second experiment, we measured manipulation kinematics. Specifically, we had participants use the objects from the first experiment to install a wire harness on a mock electrical cabinet shown on the right. Moreover, the manipulation task was segmented into specific steps so that we could later on one-to-one compare the kinematics of reach and grasp and the kinematics of manipulation of the different tools. To extract these synergies, one typically uses singular value decomposition after setting up your data matrix. Here, I have set up the matrix such that the columns are relative joint angles of the 23 measured hand joints and rows are different time-stamped observations. Doing so gives the right eigenvectors V as a particular hand postural synergy. For example, the power grasp as shown previously. Then the left eigenvectors, U, gives temporal weightings of these postures. You can think of these as gains of the postural synergy given in V. For example, the power grasp may say that all of your joints open and close simultaneously with a temporal gain that will say how open or closed the hand is. Finally, the diagonal matrix, sigma, gives a measure of the variance accounted for by a given postural synergy. You can think of this as an importance measure, where the lower order synergies are those that have the most variance accounted for and are most representative of the data. Next, it is important to highlight that I have set up my data matrix in 4 ways. The first of which was a data matrix that included all the Richer-Grass data and separately all the manipulation tasks. Then, to be able to compare synergies from Richer-Grass of one tool to the manipulation of that tool, I separated the data matrices to include kinematics when handling specifically just that tool. Namely, I separated out Richer-Grass of the zip tie to compare to manipulation of the zip tie, Richer-Grass of the scissors to compare to manipulation of the scissors, and Richer-Grass of the screwdriver to compare to manipulation of the screwdriver. So the first question was, do synergies emerge? The way we generally answer this is by looking at the reduction in the degrees of freedom using the variance accounted for, or VAF for short. Shown in these graphs here, we see the variance accounted for as a function of synergy for each of the 4 ways we extracted the synergies. That is by the all tools, just the zip tie, just the scissors, and just the screwdriver. We see Richer-Grass synergy in gray, and the manipulation synergies in red, where the bars denote the variance accounted for by a specific synergy, where synergies are ordered by decreasing variance accounted for, and the lines are the cumulative sum of the variance accounted for. Note here, we only see the first 10 synergies. The cyberglove collected kinematic data on 23 joint degrees of freedom, therefore there can be up to 23 synergies. However, here I have ignored the latter 13 degrees of freedom for graphical reasons. However, this brings us to an important point, which is that from these graphs, you can see that we get a large amount of variance accounted for with much less than 23 joint degrees of freedom. Rather, 2 to 7 synergistic degrees of freedom are enough. Thus, we can say yes, synergies do emerge. However, when we look more closely at the shown cumulative variance accounted for curves, we see that in the all tools, zip tie, and screwdriver case, we see a noticeable difference in the cumulative variance accounted for between the Richer-Grass in gray and the manipulation in red. And in fact, what some people do to account for these differences is that they quantify what is called the number of significant synergies. The number of significant synergies is determined by a cutoff metric for the number of synergies required to achieve a certain criterion. One such metric that has been used throughout the literature is the 90 and 5 method, which is the number of synergies where you have 90% variance accounted for and where adding an additional subsequent synergy does not add an additional 5% variance accounted for. Shown here are the number of significant synergies for the 4 Richer-Grass and manipulation data sets. And a two-way ANOVA of this data showed a significant effect of experiment and post-hoc Bonferroni corrected t-test revealed a significant difference in the number of significant synergies between the Richer-Grass and manipulation of the all tools data, the zip tie data, and the screwdriver data, where the manipulation case required more significant synergies to sufficiently describe the data. However, this was not the case for the scissors data, and this is a nice intuitive result. If you think about putting your hand in a set of scissors, the scissors can strain the motion of the hand, which is why you may see the same number of synergies during Richer-Grass and manipulation. Now, if you juxtapose this to the screwdriver, you may grasp the screwdriver with a lateral pinch grasp. However, when screwing a screwdriver, you'll use a finger gating motion. And this involves a lot of joint individuation, which ultimately leads to more synergies. So summarizing, in this slide we covered a lot. However, the key takeaway is that yes, we do see a synergistic reduction in the degrees of freedom in both the Richer-Grass and manipulation of these tools. However, we need more synergies to sufficiently describe manipulation than we do Richer-Grass. So given that synergies emerged in both Richer-Grass and manipulation, the next question was, are Richer-Grass synergies and manipulation synergies the same? One way to answer this question is by looking at cosine similarity. The cosine similarity is a measure of the angle between two vectors. You can think of synergies as vectors in the hyperspace. So if the vectors are collinear, the angle between them is 0, and the cosine of 0 is 1. So if two vectors have a cosine similarity of 1, that means the vectors span the same subspace. On the other hand, two vectors can be completely orthogonal, meaning the angle between them is 90 degrees, and the cosine of 90 is 0. so the cosine similarity is 0. Thus, these two vectors span orthogonal subspaces. And the same logic can be extended to matrix multiplication, where if you have a synergy matrix times another synergy matrix, then if and only if these two synergy matrices are the same, we'll end up with a cosine similarity matrix that looks like the identity, where we have ones on the diagonal and zeros everywhere else. So this matrix multiplication is exactly what I did. The cosine similarity matrices are shown here for representative subject, again separated for the 4 ways we extracted the data. That is the all tools, the zip tie, the scissors, and the screwdriver. In these cosine similarity matrices, you have zeros denoted by white values and ones denoted by black values. If the synergies between the regress and manipulation were the same, we would see black all along the diagonal and white everywhere else. And clearly, this is not what we observed. Generally, we observe high similarity in these lower order synergies, that is the first couple of synergies with high variance accounted for. But when we look at the higher order synergies, that is synergies 5, 6, and 7, and 8, the similarity tapers off. And in fact, this trend is consistent across multiple subjects. Shown here is the diagonal cosine similarity values, which I coined similitude, plotted for all the subjects as a function of synergy order. When we fit a linear model to this data, in all 4 cases, we observe that there is a significant decrease in cosine similarity as we increase synergy order. To say more plainly, these higher order synergies, that is synergies 5, 6, 7, and 8, are highly dissimilar when we compare regress and manipulation. Taking a step back and relating this to the literature, what people have previously concluded from largely studying grasping is that these higher order synergies, that is 5, 6, 7, and 8, are not important. So they just ignore them when doing their dexterity research. However, 2 slides ago, I showed that these higher order synergies are in fact important for manipulation. Now, one could say, okay, well, we have this wealth of data in reach and grasp, why don't we just apply those higher order reach and grasp synergies to manipulation? Well, on this slide, we say that you can't do this because these higher order synergies are significantly different between reach and grasp and manipulation. So what are the key takeaways from this work? First, we showed that synergies do exist when the human hand is used to manipulate a tool or complex object. However, the manipulation task requires more synergies to sufficiently describe the motion than the reach and grasp task. Then we showed that reach and grasp hand synergies and manipulation hand synergies differ, and this difference becomes more pronounced when we compare the higher order synergies. And circling back to the picture we showed before, I believe this work is important for the design of dexterous robots that aim to replicate human capabilities. You can imagine that if we use the study of grasping to make a robot that would assemble a complex wire harness, we might not design our robot using a subspace of control that is efficient for the required task. Which brings me to my final point. If we want to emulate hand function, we must study functional hand manipulation, not just grasping. Thank you for watching this video. You can find a link to the paper in the video description below. And as always, feel free to scan the QR code on the screen to connect with me on LinkedIn.